Typically, they're all 1. We then shift the sequences to fit within our bit group. We group the sequence into 4-bit chunks, and then we come up with hexadecimal representation. So with CRCA, what we are going to be representing is hexadecimal D5. Hexadecimal D5 is 5. D is 10, 11, 12, 13. So 13 times 16 plus 5. That becomes a representation of this. Where do we use CRCA? Digital satellite TV. So you see every one of these, depending on the CRC method, has a particular use. Telecom users use CRC12. CRC16 is for USB, Universal Serial Bus. And Bluetooth uses CRC32, CRC16, and Ethernet. Ethernet has CRC built into it. Remember we spoke earlier tonight about error checking, the frame check sequencing that they do when you see CRC. Now you can tell them it's based on CRC32. What I want you to understand about this is that depending on the CRC method, you can have 8, 12, 16, 32, regardless, depending on what the common use is. There is a corresponding generating polynomial. What they receive is going to be divided by the generating polynomial. If the sender and receiver both catch the same value, no errors, life is good, move on to the next one. So with CRC, take a look why just a notch above everything else. Whether you're doing single bit errors, which is the parity bit. Remember we spoke about the first time? 100%. We cannot argue with that. That means we can detect every kind of error. Double bit errors, we said that single bit could not do it. When 2 bits were modified, 100% if the generating polynomial has at least 3 ones, which they all do, so that's not an issue. Or even if it's odd number of bits in the error, also 100 bits. And again, depending to what the formulas are here, you don't need to memorize these formulas. Bottom line is the error detection performance of CRC is at or near 100%. In fact, that's how Ethernet does it. That's how satellite TV does it. Where did you go? Fine. That's how satellite TV does it. That's how Ethernet does it. Ethernet is the network communication technique. We incorporate America and everybody else in fact. Okay, so we went through all these laborious techniques. We spoke about 4 of them: single bit, double bit, arithmetic checksum, CRC. Hopefully everybody remembers those 4. Alice receives this stuff from Bob. What is Alice going to do? 3 things. Do nothing. You might say, that's crazy, but it is one way to do this. Which means I don't do anything with error, I just simply throw it out. Whether it's a frame or packet, frame at layer 2, packet at layer 3. Remember this. I want to make sure everybody understands this. Frame at the layer 2, which is data link.
Packet at IP layer.
That's correct. Packet is at layer 3, which we are dealing with IP layer, network layer. Believe it or not, network do nothing is one option that you're going to see. For example, if you're dealing with frame relay network, up until a few years ago, frame relay used to be a popular type. Now I have not seen it much being used. That's what layer 2 they did. They just dropped the packet or allowed other upper layers above layer 3, layer 4, 5, and 6 handle the error. You might have to potentially go back and return an error message, which means Alice is going to tell Bob, I've received an error message. Or, by itself, Alice is going to fix it. We're going to talk about all three of these. We're probably not going to get to every one of them today, but we're going to cover the majority of them. So again, somebody might say, crazy, you don't want to do anything. As I just mentioned to you, frame relay is one example. Frame relay detects an error. What do? They toss the frame. They hope that higher levels application layer is going to fix it. Doesn't even bother loading, Alice does not even bother notifying Bob. So the higher levels TCP/IP is going to fix it. That's the way frame relay works. Next one we talk about is to return a message. That means Alice detected there was an error. Alice is going to return back a message to the person who actually transmitted. There are two ways it's going to be returned. One is called stop and wait. I'll stop, wait to receive confirmation. You're going to see some figures of this. The other one is what's called sliding window. As we go along, maybe I confirmed 3 packets. Now I'm going to go 4 packets. The other says slow down, so I might go down to 2 packets, so on and so forth. That's what I mean by sliding window. So let's talk about stop and wait. By far, stop and wait is the easiest, the simplest of all the error control protocols. As the term implies, I send a frame, that's Bob, the transmitter. I stop, I wait till somebody sends me an acknowledgement. Acknowledge is a situation where Alice is going to tell Bob, I received. Acknowledgement itself is 2 types. Positive acknowledgement, negative acknowledgement. Positive acknowledgement is called ACK. ACK is called ACK. When you take the Wireshark, remember we showed earlier today? And you're analyzing what's being sent from Bob to Alice, you could see an ACK frame. That's exactly what it is. That's when Alice is telling Bob, yes, I received it, send me the next one. Send me the next frame. This frame was okay, send me the next frame. If Alice sends a negative acknowledgement, which we call it NAK, Bob is going to retransmit the same thing. Okay? So, ACK, depending on whether the target has an ACK or NAK, either the same frame is being sent, or a new follow-on frame is going to be transmitted. That's the idea of stop and wait. So how does this actually work graphically? This is a very simple a very sample dialogue of stop and wait. What do I mean by stop and wait? So station A, which is Bob, sends the data. Alice, which is station B, receives the data. Data arrives without an error. So what is Alice going to do? Alice is going to send an acknowledgement, which comes in the form of an ACK, right here. So ACK arrives here. Station A says, okay, everything's great, everything's hunky-dory. I'm going to send my next data. So data goes across, data arrives, but Station B somehow calculated, hopefully through CRC, what the error was, but what is it going to send instead? Instead of sending an ACK, it's going to send a NAK, a negative acknowledgement. Okay? Because it's sent, because now the NAK arrives here, what is Station A going to do? Station A is going to send the data. Well, what data is that? This data is actually the same data that was sent here. Why? Because it's received back. Everybody got that? Then there is ACK. So maybe I should do this. This is data 1, I call it. Because I receive ACK, what's going to go is data 2. Because I receive an ACK, this is also going to be data 2. Everybody got that? So the next one, which we'll talk about, is called sliding window error measurement. This, first of all, assumes that we are going to be transmitting, we are going to be sending multiple frames at any one time. So if you're going to be sending multiple frames, somehow, somewhere, the target needs to say, I received all those frames, or one of them did not arrive, I'm going to hold it in my memory, in my cache, until you resend me what's missing. So here you're dealing with what we call a sliding window. Why do we call it a sliding window? Because it allows the sender to send a number of packets at any one time without waiting for acknowledgement for a single one. What was the disadvantage here? One piece of data, one acknowledgement. One piece of data, one acknowledgement. At the surface, at the high level, this is not too efficient by itself. So what we want to do, depending on our window size, we want to be able to send multiple pieces of data and receive an acknowledgement. So when the receiver acknowledges, what happens? The ACK that goes back, the acknowledgement that goes back to Bob says, what's the number of frames I expect next? So let's proceed in action. Again, we have station A, Bob, station B, C, on Alice on the right-hand side. Bob sends the data. In this case, it sends 3 pieces of data, 0, 1, and 2. We don't care what's inside the data. It could be anything. That's immaterial. Alice receives the data, hopefully without error. How is Alice going to tell Bob, send me the next one? Not only sends an ACK, but sends what? 3. Why 3? Because 3 is the next piece of data in the sequence. Sequence says 0, 1, 2, 3. Sliding window says, okay, I received 3 of them without error. Go ahead and send me the next one. We're going to talk about errors in between as well in the upcoming slides. Hopefully this is clear to everybody thus far. So with older protocols of this sliding window, every frame or every packet was numbered. In the modern sliding window protocols, they number each byte within a frame. So here is an example. Here we're dealing with normal transfer. When we say normal transfer, that means we do not deal